In this video, I'll introduce some common errors that can arise when conducting statistical inference. There are two types of errors we can make when performing a hypothesis test, type 1 and type 2 error. We commit a type 1 error if we reject the null when in fact it's true, a false positive. On the other hand, we commit a type 2 error if we fail to reject the null when in fact it's not true, a false negative. In hypothesis tests, the type 1 error rate is represented by alpha, the significance level. This is the main reason why we use the rule of p-value being less than alpha in our testing conclusion to reject or fail to reject the null. We want to control the type 1 error rate in our experiment. We denote the type 2 error rate with the symbol beta. This class of error has a particular role in our hypothesis test as it's the complement of the power of the test. In an ideal situation, we have a hypothesis test with no error. However, the randomness from our samples makes this highly unlikely. The type 1 and type 2 error rates are inversely related, meaning that as one increases, the other decreases. Typically, we fix the type 1 error rate by choosing alpha and try to minimize beta as much as possible. This is done because in practice, making a type 1 error is usually considered more dangerous than making a type 2 error. To further understand the concept of type 1 and type 2 errors, imagine you're the judge of a criminal trial and you need to make a decision on whether or not a defendant is guilty. What are the potential types of errors in judgment you could make? If the defendant is not guilty, the type 1 error would be finding them guilty, a false positive. However, if the defendant is guilty, the type 2 error would be finding them not guilty, a false negative. The power of a test, 1 minus beta, is the true positive rate. In other words, it's the probability of correctly rejecting the null when it should be rejected because it's false. There are adjustments that can be made that affect the power of a statistical test. The larger the sample size, the larger the power of the test. The larger the significance level, the larger the power of the test. Nevertheless, this implies the test might be more prone to committing type 1 error. A larger effect size results in an increase in statistical power, although we can't usually control this in practice. These are all key factors that come into play when trying to maximize the power of the test. The p-value is an important part of hypothesis testing. Nonetheless, there are misunderstandings about it. The misuse of p-values in scientific research includes cherry-picking data in order to get a significant result in a given statistical study. We have to avoid a practice known as p-hacking. Imagine someone fishing in a lake with a lot of fish. The idea is that if you keep fishing long enough, you're bound to catch something. P-hacking involves performing many different tests on our data to obtain any significant result to publish. By doing this, multiple testing occurs, which inflates our type 1 error rate, unless we control for it with some available corrections such as Bonferroni. Another p-value related issue is something called double dipping. If we look at all of the data, we might be tempted to do some EDA to generate hypotheses of interest, and then use that same data to test our hypotheses. The consequence of this is our p-values are no longer controlling for the type 1 error rate, and results could be misleading. To avoid double dipping, we can split our data into training and testing sets, and use the training data to perform EDA and generate hypotheses that can be evaluated on the test data. The motivation of this is similar to that of machine learning, where we want to avoid data leakage so we're not cheating and using the same data to train and test a model. Anyways, I hope this video introduced some potential errors in inference that can arise and makes you think critically when you're conducting statistical inference.